The telescope array in Hawaii records light that left its source 4 hours ago. The pixels accumulate photons one at a time, building an image from almost nothing, from the faint reflected glow of something moving through the outer solar system where sunlight barely reaches. The astronomers flag it automatically moving object, unknown designation, unusual trajectory. They assign it a temporary identifier, a string of numbers and letters that will follow it through every database, every observation log, every paper that tries and fails to explain what it is. For now, it's just a smudge, a dot, a presence where emptiness should be. The computers calculate its position against the fixed stars. They measure its apparent motion across the sky, frame by frame, hour by hour. The dot moves, but not the way asteroids move, not the way comets move, not the way anything moves when it's caught in the sun's gravitational architecture. The trajectory bends wrong. The speed accumulates in ways that orbital mechanics can't accommodate. Someone runs the numbers twice, then 3 times, checking for instrument error, checking for software glitches, checking for the 1,000 small mistakes that can turn ordinary rocks into impossible objects. The numbers don't change. The object maintains its course, hyperbolic and unbound, arriving from somewhere else entirely. They name it 3I/Atlas, the third confirmed interstellar object, discovered by the Asteroid Terrestrial Impact Last Alert System. The name sounds clinical, bureaucratic, like naming a storm or a distant nebula, but the designation carries weight. Interstellar means not from here. Interstellar means it crossed the space between star systems, the light years of vacuum where nothing survives, where radiation strips away volatiles and cosmic rays break down complex molecules over millions of years of travel. Only took several million years to get here. Only crossed distances that light itself needs years to traverse. Only arrived at this exact moment in human history when telescopes exist to see it. The first spectrum arrives 3 days later. The light passes through a prism, separating into constituent wavelengths, revealing the chemical signature of whatever surface reflects the sun's distant glow. The astronomers expect water ice, maybe with carbon compounds, maybe with silicates, the standard mixture of interstellar matter, the debris that condenses between stars. Instead, the spectrum shows absorption lines that don't quite match the library of known materials, too much reflection in certain wavelengths, too little in others, a flatness across the visible spectrum that suggests something dark and uniform, but with bright patches in the near-infrared that suggest something else entirely. The spectrum doesn't resolve into coherent composition. It fragments into possibilities, each one requiring conditions that seem unlikely in interstellar space. The brightness varies as it tumbles, every few hours. The reflected light dims and brightens in a pattern that suggests rotation, but an unstable rotation, a tumbling motion that implies asymmetric shape, uneven mass distribution, something that doesn't spin like a sphere or even like an elongated ellipsoid. The light curve shows sharp peaks and deep valleys, brightness changes of several magnitudes that would require extreme geometry, something long and thin, or something with reflective and dark sides, or something with surface features that catch and release sunlight in ways that natural erosion rarely produces. The tumbling has no obvious period. It shifts, gradually, as if the object responds to forces the instruments can't detect. They publish the initial findings in a circular, a brief technical report distributed through astronomical networks. The language stays careful, measured, describing observations without interpretation, listing measurements without drawing conclusions. But the numbers speak for themselves. Hyperbolic excess velocity significant, surface composition anomalous, shape highly elongated, origin unknown. The circular ends with a call for additional observations, an invitation for other telescopes to track this object while it remains visible. While it passes through the inner solar system on its one-time transit, its single crossing of our local space before continuing outward into darkness that swallows everything. The orbital elements arrive in spreadsheets, in tables of numbers that describe curves through space. Eccentricity greater than 1, the defining characteristic of hyperbolic trajectories, of objects that fall toward the sun and then escape, never to return. The semi-major axis becomes meaningless, undefined for paths that don't close. Instead, the calculations focus on perihelion, the closest approach, the moment when 3I/Atlas swings nearest to the sun's warming influence before accelerating outward on the far side of its arc. The computers trace the path backward, rewinding the motion through years of travel, projecting where this object came from before it entered the solar system's gravitational influence. The origin point dissolves into uncertainty. Trace the trajectory back far enough and the errors compound. The small uncertainties in velocity and position multiplying across light years until the probable source region spans dozens of cubic parsecs. No obvious stellar home, no nearby star along the incoming vector. The galactic neighborhood around that origin point contains mostly empty space, a few red dwarfs, a scattering of brown dwarfs too dim to see without infrared instruments. Nothing that could have ejected this object with enough velocity to send it wandering between stars. Nothing that explains where it came from or why it travels alone. The velocity itself poses questions. Interstellar objects should move at speeds typical of the local standard of rest. The average velocity of stars in this region of the galaxy, about 20 kilometers per second relative to the Sun, 3I/Atlas moves faster. Not impossibly fast, not relativistic, but fast enough to suggest acceleration from some past event ejection from a stellar system during planetary formation. Perhaps, or gravitational slingshot around multiple bodies, or some encounter with a rogue planet in the darkness between stars. The excess velocity implies energy, implies violence in its history, implies forces that threw it into the void with enough momentum to carry it across interstellar distances without slowing, without stopping, without settling into any stable orbit. The astronomers calculate the object's future trajectory. It will pass perihelion in approximately 40 days, swinging inside Earth's orbit, though not close enough to pose any threat, not close enough to perturb planetary motions or rain debris onto the inner worlds. After perihelion, it will accelerate outward, climbing back up the sun's gravitational well, heading toward the outer solar system and then beyond, toward the heliopause where the solar wind fails, toward the Oort cloud's distant shells, toward the interstellar medium it crossed to arrive here. In 200 years, it will exit the region where the sun's gravity noticeably affects motion. In 10,000 years, it will travel farther from the sun than any object humans have ever tracked. In 1,000,000 years, it might pass near another star, might fall into another system, might repeat this entire process in reverse under different skies. The mathematics describes motion without explaining it. The equations predict position at any given time, forecast where telescopes should point to capture the next image, calculate Doppler shifts and proper motion and all the quantities that turn observation into understanding. But the equations only describe what happens, not why it happens this way, not why this particular object follows this particular path at this particular time. The uncertainty nags at the teams reviewing the data. They check for computational errors, for mistakes in coordinate transformation, for bugs in the orbital integration software. The numbers remain stable, the trajectory holds. Only a hyperbola, only the simplest possible escape path, only the geometry that gravity demands for unbound objects, yet somehow it feels wrong. The observations accumulate in archives, in databases that store terabytes of astronomical data. images and spectra and photometry from telescopes across the globe. Different instruments track 3I/Atlas as it brightens with approaching perihelion, as the sun's increasing warmth should trigger outgassing if any volatile ices hide beneath the surface. The teams coordinate timing, sharing target coordinates, maximizing coverage to catch any transient events, brightness spikes, color changes, coma formation, any sign that this object responds to heating the way comets respond. They watch in shifts around the clock, pointing instruments at this moving target that refuses to behave like natural objects should behave. Only a few dozen interstellar objects probably pass through the inner solar system each year, undetected, untracked, invisible against the overwhelming background of local debris. Only improved survey instruments made finding 3I/Atlas possible, made tracking its motion feasible across the months of its passage. Only the last decade of technological advancement gave humanity the tools to notice visitors from beyond, to measure their properties, to ask questions about their nature. Before that, they passed unseen, unrecorded, leaving no trace in human knowledge, travelling through a solar system that contained no observers capable of recognizing them for what they were. The next observation window opens in 72 hours. The object will be marginally closer, marginally brighter, positioned against darker sky where background stars don't contaminate the signal. The teams prepare their instruments, calibrate their detectors, submit observing proposals to allocation committees who decide which objects deserve telescope time. 3I/Atlas receives high priority. Interstellar objects don't visit often. The opportunity to study one up close, to gather data while it remains visible, won't come again in this generation. They prepare to look more carefully, to see what the next images reveal, to learn whether the anomalies resolve into normal physics or deepen into something stranger. The light that reaches Earth left the object's surface minutes ago, travelling at 300,000 kilometers per second, crossing the void as electromagnetic waves, as photons that carry information encoded in their wavelengths, their polarization, their arrival times. The telescope mirrors collect these photons, focusing them through optical systems that concentrate faint signals into detectable intensities. The light passes through filters, through spectrographs that spread wavelengths into rainbows of data, through sensors that convert photons into electrical signals, into numbers that computers store and analyze and transform into knowledge. The spectrum puzzles the spectroscopists. They compare it against reference libraries containing thousands of materials, minerals, ices, organic compounds, metals, everything that telescopes have identified on asteroids and comets and planetary surfaces across the solar system. Nothing matches exactly. The overall reflectance suggests a dark surface, something that absorbs most visible light, returning only a small fraction to space. But certain wavelengths show unexpected brightness. Reflection peaks where dark materials should show absorption valleys. Water ice produces a characteristic absorption at 3 micrometers. Carbon compounds create features around 3.4 micrometers. Silicates show strong signatures between 8 and 12 micrometers. 3I/Atlas shows all of these features, but weakly, ambiguously, as if multiple materials coat the surface in patches, or as if some unknown substance mimics the spectral properties of familiar materials without actually being those materials. The polarization measurements add another layer of confusion. When light reflects off a surface, it gains polarization, becomes oriented in specific directions depending on the surface texture, the grain size, the refractive index of the material. Smooth surfaces produce different polarization than rough surfaces. Icy surfaces produce different patterns than rocky surfaces. The polarization from 3I/Atlas varies across wavelengths in ways that suggest multiple surface types, or variable surface properties, or some combination of materials that don't normally occur together on natural bodies. the degree of polarization reaches values typical of fine dust. But the wavelength dependence suggests larger particles, centimetre-scale roughness, texture that contradicts the dust hypothesis. They attempt thermal modelling, trying to predict what temperatures the surface should reach at various distances from the Sun. The models assume standard thermal properties: heat capacity, thermal conductivity, emissivity, and calculate how sunlight warms the surface, how heat radiates away into space, how temperature varies between the illuminated day side and the shadowed night side during the object's tumbling rotation. The predicted temperatures should guide observing strategies for infrared telescopes, should indicate which wavelengths will reveal the most information about surface composition. But the models struggle with the unknown geometry, the uncertain shape, the possibility that extreme elongation creates complicated patterns of heating and cooling that simple spherical approximations can't capture. The first infrared observations arrive from a telescope in Chile. The infrared reveals heat, shows thermal emission from surfaces warmed by sunlight, provides temperature measurements independent of reflected light. The data shows temperatures lower than the models predict, significantly lower, as if the surface doesn't absorb sunlight efficiently, or as if heat conducts into the interior rather than staying near the surface, or as if some portion of the incident energy escapes through processes the models don't include. The temperature distribution across the rotation cycle shows unexpected patterns: warm spots where shadows should fall, cool regions where sunlight strikes directly. The thermal maps don't make geometric sense. They suggest surface properties that vary spatially, regions with different thermal responses, materials arranged in patterns rather than mixed randomly the way impact gardening typically arranges surface regolith. Only photons carry information across space. Only electromagnetic radiation bridges the enormous distances, bringing messages encoded in frequencies and intensities and polarization states. The object itself remains unreachable, untouchable, forever separated from human instruments by millions of kilometers of vacuum. No spacecraft travels fast enough to intercept it. No probe launches quickly enough to catch an object moving at interstellar velocities on a hyperbolic escape trajectory. The only tools available are photons, the ancient light that bounced off something strange and travelled through emptiness to reach detectors designed to decode its secrets. Only light, only the oldest messenger. Only the method that astronomy has always used to study things it cannot touch. The spectroscopists write their reports carefully. They describe anomalies without claiming understanding, list measurements without forcing interpretations, acknowledge uncertainties without dismissing them. The spectrum defies simple explanation. The thermal properties don't match predictions. The polarization suggests complexity. They end their reports with recommendations for additional observations, more wavelengths, longer exposures, better signal-to-noise ratios. They suggest coordinated campaigns, multiple telescopes observing simultaneously to catch time-variable phenomena, to separate intrinsic changes from instrumental artifacts. They propose polarimetric studies, phase curve photometry, high-resolution spectroscopy if the object brightens enough at perihelion. They request time on larger telescopes, instruments with better sensitivity, facilities that can probe fainter signals and detect subtler features. The light continues arriving, photon by photon, building information at the speed that observing allows. Each wavelength adds constraints, narrows possibilities, eliminates hypotheses that don't match the data. Each measurement refines the understanding, even when that refinement reveals deeper mysteries rather than simple answers. The object tumbles through space, reflecting sunlight according to physical laws that don't change with human confusion, exhibiting properties that follow from its actual composition and structure, even if observers can't yet determine what these properties mean. Only nature knows what this thing is made from. Only time, and more observations, might reveal whether the strangeness resolves into familiar categories or persists into genuine anomaly. The resolution improves as the object approaches perihelion. What began as a single pixel, a point of light indistinguishable from background stars except for its motion, now spreads across multiple pixels, begins to show structure, begins to reveal shape. The adaptive optics systems compensate for atmospheric turbulence, correcting the wavefront distortions that blur ground-based observations, sharpening the image to near diffraction limits. The Hubble Space Telescope adds its view from above the atmosphere, from orbit where air doesn't shimmer and distort, where long exposures accumulate signal without atmospheric interference. The images stack and combine, averaging out noise, bringing faint details above detection thresholds. The shape emerges slowly, pixel by pixel, frame by frame across multiple observation sessions, elongated. Certainly the brightness variations during rotation already suggested that, but the degree of elongation exceeds expectations. The aspect ratio reaches 10:1, perhaps higher, a cigar-shaped profile that tumbles end over end, presenting different cross-sections to Earth's viewing angle as it rotates through complex motion. Natural objects rarely maintain such extreme geometry. Collisions tend to shatter elongated bodies. Tidal forces break apart structures that extend too far from their center of mass. Spin rates generate centrifugal stress that pulls material apart when aspect ratios become too large. Yet 3I/Atlas holds together, maintains its shape, tumbles through space without flying apart or crumbling into fragments. The surface features appear gradually as resolution increases. At first, just brightness variations, some regions reflect more light, some absorb more, creating a mottled appearance that suggests compositional heterogeneity or topographic relief. Then, as the images sharpen, patterns emerge, linear features, boundaries between bright and dark regions that run parallel across sections of the surface. Patches of uniform albedo arranged in geometric configurations that look almost regular, almost intentional. The features don't appear natural, don't resemble the chaotic cratering and space weathering that mark asteroid surfaces. They look organized, arranged, positioned according to some logic that random impacts never produce. The imaging team reviews the data carefully, checking for artifacts, for processing glitches that might create false patterns. They examine individual frames before stacking, looking for consistent features that appear in multiple independent observations. They rotate the image orientation, apply different enhancement techniques, vary the contrast and brightness scaling to ensure the patterns aren't illusions created by human pattern recognition, imposing order on random noise. The features persist. They appear in multiple wavelengths, show up in infrared observations as well as visible light, remain present across different viewing geometries as the object's rotation presents different faces toward Earth. The features are real, whatever they are. They exist on the actual surface, represent genuine structure in the object's physical form. The published images spread through astronomical networks within hours. Other researchers download the files, analyze the data independently, attempt their own reconstructions and enhancements. Some see the patterns clearly, measure the feature sizes, calculate their spacing and orientation. Others remain skeptical, argue that low resolution and limited signal-to-noise allow multiple interpretations, suggest the features might be natural formations viewed at angles that create false impressions of regularity. The debates begin in email threads, in online forums, in conversations at conferences where astronomers gather to discuss unexpected discoveries. No consensus emerges. The images provoke questions without providing answers, reveal details that demand explanation without offering obvious mechanisms. Only the light captured during those observation sessions preserves what the surface looks like. The object continues moving, continues tumbling, presenting new faces that might look completely different, might show different features or no features at all. The rotation period remains uncertain. the tumbling motion too complex to predict reliably from limited observations. The next imaging session might catch a completely different hemisphere, might show smooth terrain or heavily cratered regions or other patterns that add information or deepen confusion. The teams plan their observations carefully, trying to maximize coverage, trying to map as much of the surface as possible before the object fades beyond the resolution limits of even the largest telescopes. The geometry poses problems for standard shape modeling techniques. The software assumes roughly spherical targets, or at least convex shapes that don't deviate too extremely from ellipsoids. The algorithms struggle with extreme elongation, fail to converge on stable solutions when aspect ratios exceed certain thresholds. The researchers adapt their methods, write custom code, implement new approaches designed for highly asymmetric objects. They build three-dimensional models from the brightness variations, from the way different features appear and disappear as the object rotates, from the shadows and highlights that indicate topographic relief. The models remain provisional, uncertain, dependent on assumptions about surface properties and albedo distributions. But they suggest something long and narrow, something that extends for kilometers along its major axis while measuring only hundreds of meters across its minor axes. Only natural processes sculpt asteroid shapes, collisions, tidal disruption, rotational deformation, thermal fracturing. The object should show signs of these processes, should exhibit the irregular profiles and fractured surfaces that impacts create over millions of years of exposure to space debris. Instead, the images show regularity, show patterns that repeat with spacing too consistent for random chance, show boundaries between regions that look sharp rather than gradational. The surface appears maintained, preserved, structured in ways that don't match the expected weathering from cosmic rays and micrometeorite bombardment. Either the object formed very recently, remained isolated from impacts during its interstellar journey, or something about its composition prevents normal space weathering effects. All three possibilities seem unlikely. The mystery accumulates in the pixels, in the patterns that shouldn't exist on something that travelled for millions of years through the radiation and dust of interstellar space. The first compositional hypothesis proposes water ice, the most common volatile in the outer solar system, the substance that forms cometary nuclei and covers the surfaces of distant moons. Water ice sublimates under solar heating, releases vapor that creates the glowing comas around comets, produces tails that stream millions of kilometers downwind from the sun's radiation pressure. The researchers calculate expected sublimation rates for 3y/8 at its current distance, predict how much water vapor should be escaping from the surface if ice composes the exterior layers. The predictions suggest detectable outgassing, measurable gas production that should appear in spectroscopic observations as emission lines from dissociated water molecules, as hydroxyl radicals that fluoresce in ultraviolet light. The observations show nothing. No emission lines, no coma, no tail. No evidence of active sublimation despite surface temperatures warm enough to vaporize water ice at rates that should produce obvious signatures. The researchers recalculate, wondering if their models overestimate the sublimation, if perhaps a dust mantle covers the ice and insulates it from solar heating. But even small exposed patches should produce detectable gas. Even fractures that expose fresh ice should create localized jets, temporary bursts of activity that appear as brightness spikes or asymmetric coma features. The object remains inert, inactive, showing no signs of volatile release even as it approaches perihelion where heating should maximize outgassing rates. The hypothesis shifts to nitrogen ice, the material that coats Pluto's surface, that forms Triton's polar caps, that survives in the coldest regions where water ice would sublimate away. Nitrogen ice requires even lower temperatures to remain stable, sublimates readily once surfaces warm above certain thresholds. differences. The calculations suggest nitrogen ice should already be vaporizing at 3I/Atlas's current distance. Should have been vaporizing for weeks as the object fell inward toward the sun's warming influence. Yet again, no gas production appears in the spectra, no nitrogen emission, no nitrogen compounds, no evidence of sublimation from a nitrogen ice surface. The hypothesis fails as completely as the water ice model, contradicted by the absence of activity that such compositions inevitably produce. The organic compounds enter the discussion next tholins, complex carbon-rich materials that form when simple organic molecules are irradiated by ultraviolet light and cosmic rays. Tholins are dark, reddish-brown, stable at room temperature, resistant to sublimation. They coat the surfaces of Kuiper belt objects, form hazes in Titan's atmosphere, accumulate in the outer solar system where sunlight drives photochemistry, but heating remains minimal. A tholin-covered surface would explain the dark albedo, might explain the lack of outgassing, could account for the strange spectral features that don't match simple ices or rocks. The model seems promising until the thermal data contradicts it. Tholins absorb sunlight efficiently, should heat up and radiate strongly in the infrared. 3I/Atlas remains too cold for a tholin surface, reflects too much light in certain wavelengths where tholins should absorb strongly. The composition doesn't fit. Only a few months of observations, and already 3 major hypotheses have failed. Only 3 attempts to explain the surface properties, and none survive contact with the full data set. The researchers return to their spectral libraries, searching for other candidates, other materials that might match the unusual combination of properties dark but not too dark, reflective in odd wavelengths, thermally anomalous, geometrically extreme. They consider mixtures, multiple materials combined in layers or patches, heterogeneous surfaces where different regions show different compositions. The models multiply, proliferate into dozens of possibilities, each one requiring specific assumptions and special conditions. None of them feel satisfying. None of them explain everything without invoking unlikely scenarios or rare circumstances. The retraction appears in a follow-up circular published 3 weeks after the initial composition estimates. The language remains technical, careful, avoiding dramatic acknowledgement of failure. The authors note that further observations have complicated initial interpretations, that the object's properties don't conform to standard compositional models, that additional data is needed before definitive statements can be made about surface materials. They withdraw their earlier suggestions of water ice. List the reasons the hypothesis fails. Describe the negative results from outgassing searches. They propose no replacement hypothesis. The circular ends with uncertainty, with acknowledgement that the composition remains unknown despite multiple investigative approaches. Other teams publish their own attempts, their own models that try to reconcile the conflicting observations. Each paper introduces new possibilities: hydrogen icebergs, fractal dust aggregates, magnetic grain alignments, exotic phase transitions in materials subjected to millions of years of cosmic ray bombardment. Each model explains some features while struggling with others. Each one requires conditions that seem improbable. Arrangements of matter that don't occur naturally in known environments. The literature fragments into speculation, into tentative proposals that their own authors hedge with caveats and uncertainties. The field loses consensus, splinters into competing interpretations that can't be resolved with available data. Only the object itself knows what it's made from. Only the atoms and molecules that form its structure, that bind together in whatever configuration produces these anomalous properties, contain the truth that observations approximate but cannot yet decode. The surface sits out there in the vacuum, real and physical and composed of specific substances arranged in specific ways, reflecting light according to immutable physical laws. The mystery exists only in human understanding, only in the gap between what instruments can measure and what theories can explain. The object has no mystery to itself. It simply is what it is, travelling through space, indifferent to the confusion it provokes in creatures watching from a small blue world it will pass once and forget. The shape reconstruction algorithms process hundreds of images, tracking brightness variations across multiple rotation cycles, building three-dimensional models from the way light and shadow move across the surface. The software assumes convex geometry at first, standard practice for objects too distant to resolve topographic details directly. The model that emerges shows extreme elongation, an aspect ratio approaching 10:1, perhaps exceeding it depending on viewing angle assumptions and albedo corrections. The shape resembles a cylinder or a prolate spheroid stretched beyond the limits where such descriptions remain useful. The long axis extends for approximately 800 meters. The short axes measure less than 80 meters across. The proportions disturb the researchers who review the results. Natural objects don't maintain such extreme geometries. The structural strength of rock and ice can't support elongated shapes beyond certain aspect ratios, particularly for objects large enough that self-gravity becomes significant. Internal stresses build up along the long axis. Tension forces that exceed material strength and cause fracturing cause the object to break into smaller, more stable pieces. Rubble pile structures might extend somewhat, held together loosely by minimal self-gravity, but even rubble piles collapse when elongation exceeds 5 or 6:1. 3I/Atlas extends further, maintains coherence despite proportions that should guarantee structural failure. Either it's made of materials stronger than any known rock or ice, or it's not actually as elongated as the light curves suggest, or something else holds it together: internal reinforcement, maybe, or rotation rates that create stabilizing forces, or composition gradients that concentrate stronger materials along stress paths. The rotation analysis reveals complex tumbling motion. The object doesn't spin around a single axis like a well-behaved asteroid. Instead, it tumbles chaotically, rotating simultaneously around multiple axes, presenting constantly changing orientations to observers. The tumbling suggests torque-free rotation, the kind of motion that develops when objects aren't perfectly symmetric, when mass distribution deviates from ideal geometry. But the tumbling also makes reconstruction difficult. The brightness variations don't repeat regularly enough to determine a clear rotation period. The light curves show quasi-periodic behavior, patterns that almost repeat but drift slightly with each cycle, suggesting precession, suggesting the rotation state slowly evolves as internal mass redistributions or external torques perturb the angular momentum. Only 2 other interstellar objects preceded 3I/Atlas through the inner solar system in recorded history. 1I/Oumuamua, discovered in 2017, also showed extreme elongation, also puzzled astronomers with its unusual shape and lack of outgassing. 2I/Borisov, discovered in 2019, looked more conventional, a clear comet with active gas production and dust emission. The sample size remains too small for generalizations. Perhaps interstellar objects naturally show extreme shapes. Perhaps the journey through interstellar space preferentially destroys more compact bodies. Perhaps only the strangest objects survive long enough to cross the galaxy and arrive at our doorstep. Or perhaps humanity has simply been unlucky, catching 3 visitors that happen to be unusual rather than representative of the true population. The images show rotation in time-lapse sequences, frames captured hours apart that reveal how the object's orientation changes, how different faces come into view and disappear again as tumbling proceeds. The linear features visible in earlier images appear in some frames but not others, suggesting they occupy specific regions rather than covering the entire surface. The bright patches concentrate along what might be the equator, or what might be structural seams, or what might be completely unrelated to the object's geometry, in ways that make sense only to the physics governing their formation. The features move across the frame as rotation continues, tracking paths that the reconstruction algorithms use to constrain the three-dimensional shape model. The density estimates require knowing both the mass and the volume. The volume comes from the shape model, uncertain but calculable from the dimensions. The mass requires either gravitational measurements, impossible at these distances, or assumptions about composition that remain unverified. If 3I/Atlas were made of water ice, it would mass perhaps 100 million kilograms. If rock, 3 times that. If metal, 10 times more. The actual mass remains unknown, hidden inside the object where no remote sensing technique can penetrate. The density affects predictions about structural stability, about whether internal strength can support the observed geometry, about how the object responds to tidal forces during close stellar encounters. Without knowing the mass, the stability calculations float in parameter space, conditional on composition, dependent on unknowns. Only gravity sculpts shapes over long timescales. Only the relentless pull toward the center of mass, the tendency for material to settle into configurations that minimize gravitational potential energy, determines equilibrium forms. Small objects can maintain irregular shapes because their self-gravity remains weak, unable to overcome material strength. Large objects collapse towards spheres because gravity overwhelms strength, forces material to flow and redistribute until the shape approximates hydrostatic equilibrium. 3I/Atlas sits in the intermediate regime where gravity and strength compete, where shape depends on composition and structure and thermal history. The extreme elongation suggests either minimal self-gravity or enormous structural strength, or formation through processes that don't involve gravitational collapse at all. The tumbling continues, indifferent to human attempts at understanding. The object rotates according to conservation laws, angular momentum preserved across millions of years of travel, rotation state established by whatever event sent it into interstellar space. The tumbling will continue forever unless external torques intervene solar radiation pressure, outgassing forces, magnetic interactions with the interstellar medium. For an inert object showing no activity, the rotation state should remain nearly constant, should preserve information about its dynamical history, should encode clues about its origin in the pattern of its motion. The researchers measure the tumbling carefully, track changes over weeks of observation, search for acceleration or deceleration that might indicate non-gravitational forces. The motion holds steady. Only rotation, only the ancient spin, only the memory of whatever violence launched this thing into the darkness between stars. The cometary activity models predict outgassing based on surface temperature, solar flux, and volatile composition. As objects approach the Sun, heating drives sublimation from exposed ices, creates pressure beneath dust mantles, generates jets that erupt from surface fractures. The gas production follows predictable curves, increases exponentially with decreasing heliocentric distance, peaks near perihelion where solar heating reaches maximum intensity. For an object the size of 3I/Atlas at its current distance, even modest ice fractions should produce detectable gas emission, should create faint coma visible in deep exposures, should show up as spectral signatures from molecules fluorescing in sunlight. The telescopes search for emission lines at wavelengths characteristic of cometary volatiles. Hydroxyl at 308 nanometers, the dissociation product of water. Cyanogen at 388 nanometers, produced from organic ices. Carbon monoxide at infrared wavelengths, sublimating from the coldest ices that survive farthest from the Sun. The spectrographs integrate for hours, accumulating photons from the target region, building signal above noise thresholds, reaching sensitivities that should detect gas production rates 1,000 times smaller than typical comets show at similar distances. The emission lines don't appear. The spectra remain flat, featureless, showing only reflected continuum light from the Sun without any contribution from glowing gases. The narrowband imaging searches for coma, for the faint halo of gas and dust that surrounds active comets, that scatters sunlight and creates extended brightness around the nucleus. The images compare on-band and off-band observations, looking for excess brightness in wavelengths where cometary emissions concentrate. The processing subtracts background stars, removes instrumental artifacts, enhances faint structures that might indicate gas production. The images show nothing beyond the point-like nucleus itself. No coma, no tail, no asymmetric brightness that would indicate jets or localized outgassing. The object appears entirely inert, inactive, showing no response to solar heating despite temperatures that should vaporize multiple volatile species. Only 3 explanations remain possible. Either 3I/Atlas contains no volatile ices at all, somehow consists entirely of refractory materials that don't sublimate at these temperatures, or the volatiles are sealed beneath an insulating mantle thick enough to prevent gas escape, a crust of dust and refractory organics that blocks heat conduction and traps internal ices. Or the object is not heated as much as the models predict, somehow maintains cooler temperatures through enhanced reflectivity or rapid rotation or surface properties that limit thermal absorption. Each explanation faces problems. Pure refractory composition seems unlikely for an object that formed in the outer regions where ices dominate. Mantles thick enough to suppress all outgassing should crack and expose fresh ice during the tumbling rotation. Thermal properties unusual enough to keep the surface cold should show up in infrared observations as anomalous temperature distributions. The non-gravitational acceleration complicates the mystery. When comets outgas, the escaping vapors exert thrust on the nucleus, create rocket-like forces that change the orbit slightly, produce accelerations detectable through precise position measurements. Oumuamua, the first interstellar visitor, showed exactly this kind of acceleration despite lacking visible outgassing, a puzzle that generated intense debate about whether invisible gases or exotic propulsion mechanisms cause the motion. 3I/Atlas also shows orbital deviations, tiny discrepancies between predicted and observed positions that grow over weeks of tracking, that suggest non-gravitational forces act on the object even though no gas emission appears in any wavelength. The trajectory refinements incorporate the acceleration, adding terms to the orbital equations that account for the anomalous forces. The magnitude remains small, barely detectable above measurement uncertainties, but present in multiple independent data sets from different observatories. The direction of the acceleration doesn't point away from the Sun as outgassing thrust should. Instead, it varies with the object's orientation, changes as the tumbling presents different faces toward the Sun, suggests forces tied to surface features rather than uniform gas production. The behavior doesn't match any standard cometary model. It doesn't match radiation pressure calculations. It doesn't match anything in the database of known solar system dynamics. The researchers publish the outgassing limits. The upper bounds on gas production rates derive from the non-detections. The limits are stringent, ruling out activity at levels far below what objects of similar size typically show. If 3I/Atlas contains water ice and that ice sublimates at the surface, less than 1% of 1% of the surface can be actively outgassing. If nitrogen ice, the fraction must be even smaller. The object is, for all practical purposes, completely inactive. It neither behaves like a comet nor shows the properties expected from an inert rocky asteroid. It occupies an uncomfortable middle ground, exhibiting characteristics that don't fit established categories. Only solar heating should drive activity at these distances. Only the increasing flux of sunlight as perihelion approaches should warm the surface, should vaporize ices, should produce the gas emission that defines cometary behavior. The heating is predictable, calculable, inescapable for objects in this orbit. Yet 3I/Atlas resists, maintains its inert state, refuses to outgas despite conditions that should guarantee volatile release. Either the models fundamentally misunderstand cometary physics, or this object follows different rules, or the surface properties differ so dramatically from known solar system bodies that standard assumptions completely fail. The lack of outgassing becomes as significant as any positive detection, an absence that demands explanation as urgently as the presence of something unexpected would. The albedo measurements quantify how much sunlight reflects from the surface versus how much absorbs into the material. Geometric albedo compares brightness at zero phase angle, when the sun-object observer angle vanishes and shadowing effects minimize. Bond albedo integrates reflection across all angles, accounts for how surfaces scatter light forward and backward, provides the total fraction of incident energy that returns to space rather than heating the interior. Both measurements require careful calibration, correction for distance and viewing geometry, modelling of the scattering properties that determine how brightness changes with illumination angle. The visible wavelength observations show low albedo, around 5 to 8% geometric reflectance, placing 3I/Atlas among the darker objects in the solar system. Charcoal reflects about 4%, fresh asphalt around 7%. Comet nuclei typically range between 2 and 6%, darkened by organic residues that accumulate as ice sublimates and leaves behind refractory dust. The low visible albedo suggests carbon-rich composition, organic materials, perhaps tholins or graphitic compounds that absorb across the spectrum. The darkness is not unusual. Many outer solar system objects show similar reflectance. The darkness alone explains nothing. The near-infrared measurements complicate the picture. At wavelengths between 1 and 2.5 micrometers, the albedo increases dramatically. The surface reflects 20 to 30% of incident light. Brightness levels incompatible with the organic materials that should dominate if the visible darkness comes from carbon compounds. The infrared brightness suggests different composition, or different surface structure, or wavelength-dependent scattering that varies across the spectrum in ways that natural weathering rarely produces. Minerals can show wavelength-dependent albedo, but the variations typically remain modest, factors of 2 or 3 at most. 3I/Atlas shows factors of 5 or more. Brightness changes that require either compositional heterogeneity or surface properties that affect short and long wavelengths through different physical mechanisms. The ultraviolet observations add another anomaly. At wavelengths below 400 nanometers, the reflectance drops even further, falling to 2 or 3%, darker than almost any known material. Organic tholins absorb strongly in the ultraviolet, but not this strongly. Ice reflects ultraviolet efficiently, completely inconsistent with the observations. Rocky minerals show moderate ultraviolet reflectance, again failing to match the extreme darkness. The spectrum shows slope, colour, wavelength dependence that doesn't match any single material, that requires mixing multiple components or invoking surface treatments that alter optical properties through processes not commonly observed in nature. Only photons at specific wavelengths carry the information. Only the light that reflects rather than absorbs. Only the electromagnetic radiation that survives the round trip from sun to surface to telescope. Each wavelength samples the surface differently. Visible light penetrates only micrometers into most materials, probes only the outermost grains, reflects from surfaces that might be coated or processed by space weathering. Infrared penetrates deeper, millimeters or centimeters depending on material, samples subsurface layers that might preserve original composition beneath altered crusts. Ultraviolet interacts strongly with organic bonds, gets absorbed by carbon compounds, destroys complex molecules through photodissociation. The wavelength-dependent reflectance maps surface properties across different depths, reveals structure in the vertical dimension that single wavelength observations cannot access. The phase curve observations track brightness as viewing geometry changes, as the angle between Sun, object, and Earth varies during the object's orbit. Brightness typically increases at small phase angles, a phenomenon called opposition surge, where shadowing effects vanish and multiply, scattered light adds coherently. Rough surfaces show strong opposition surge. Smooth surfaces show weak surge. The phase curve shape reveals surface texture, grain size, particle packing, the microscale structure that determines how light bounces between grains before escaping. 3I/8LAS shows unusual phase behavior. Brightness variations that don't match standard models, surge characteristics that suggest both rough and smooth terrain depending on wavelength. As if different surface regions dominate the reflection at different colors, the polarization measurements reveal even more strangeness. Reflected light becomes polarized when it bounces off surfaces, with the degree and direction of polarization depending on composition and texture. At visible wavelengths, 3I/Atlas shows high polarization, values typical of fine dust or rough regolith. At infrared wavelengths, the polarization nearly vanishes, suggesting smooth surfaces or larger particles. The wavelength dependence of polarization doesn't match the wavelength dependence of albedo. The two properties should correlate, both determined by the same surface characteristics. The mismatch suggests layered structure, multiple surfaces at different depths contributing differently at different wavelengths, or anisotropic materials that scatter light through different mechanisms in different spectral regions. Only surface properties determine how light interacts with matter. Only the arrangement of atoms, the structure of crystals, the packing of grains, the roughness of texture determines which photons reflect and which absorb. The surface is real, physical, composed of specific materials with specific optical constants. The strange albedo variations must follow from actual physical structure, must result from real configurations of real substances, even if those configurations seem unlikely or unprecedented. The surface doesn't know it's anomalous. It simply exists, scatters light according to electromagnetic theory, produces the reflectance spectrum that telescopes measure and models struggle to explain. The published albedo values come with large error bars, uncertainties that span ranges wide enough to accommodate multiple interpretations. But even accounting for uncertainties, the wavelength dependence remains extreme. The variations too large to explain through normal processes. Either 3I/Atlas formed under unusual conditions, or its surface has been modified by exposure to environments that don't exist in the solar system, or the optical properties result from structure or composition that nature rarely produces without assistance. The albedo is not evidence of anything specific, but it is evidence that something about this object differs fundamentally from the population of asteroids and comets that orbit the Sun in ordinary fashion, following ordinary paths, obeying ordinary physics in ordinary ways. The infrared telescopes map thermal emission across the object's rotation cycle, building temperature profiles that should reveal how solar heating distributes across the surface. The models predict simple patterns, highest temperatures where sunlight strikes most directly, coolest temperatures in shadow or on faces pointing away from the Sun. Gradual variations as rotation carries different regions through day and night. The thermal inertia of the surface material should determine how quickly temperatures respond to changes in illumination, how much heat conducts into the interior versus radiating immediately back to space. Rocky materials show high thermal inertia, warm slowly and cool slowly, maintain elevated temperatures even after sunset. Fluffy dust shows low thermal inertia, heats and cools rapidly, tracks illumination changes almost instantaneously. The temperature maps don't match the predictions. The hottest regions appear in locations that should be shadowed based on the shape model and rotation state. Cool patches persist in areas where direct sunlight should maximize heating. The temperature distribution shows spatial structure. Discrete zones with different thermal properties. Boundaries between regions that remain sharp rather than gradational, as heat conduction should smooth them. The thermal inertia derived from the observations varies across the surface by factors of 10 or more, suggesting dramatic changes in material properties over small spatial scales, or topographic features that create complex shadowing patterns, or something about the surface composition that affects thermal behavior in ways the models don't capture. The subsolar temperature, the maximum temperature reached at the point where sunlight strikes, most directly measures lower than predictions by 30 or 40 degrees Kelvin. At this distance from the Sun, exposed surfaces should reach temperatures around 240 Kelvin, warm enough to sublimate water ice rapidly, hot enough to drive significant thermal emission in mid-infrared wavelengths. The observed temperatures barely exceed 200 Kelvin, colder by margins that can't be explained through calibration uncertainties or modelling errors. Either the surface reflects more sunlight than the albedo measurements suggest, or heat escapes through mechanisms beyond simple thermal radiation, or the material possesses thermal properties unlike any substance in the spectroscopic databases. Only energy balance determines surface temperature. Only the equilibrium between absorbed solar flux and emitted thermal radiation sets the steady-state value that surfaces reach under constant illumination. The equations are straightforward. Basic physics that works for every planet and asteroid and comet ever observed. Solar flux in equals thermal flux out, plus whatever energy conducts into the interior or escapes through sublimation. For 3I/Atlas. The observed temperatures require either much higher reflectivity than the visible albedo suggests, or enhanced thermal emission through some unidentified process, or heat removal through mechanisms that don't involve radiation at all. Each possibility contradicts other observations. Each explanation requires abandoning established relationships between measurable quantities. The diurnal temperature variations, the changes in temperature as rotation, carries surfaces from sunlight into shadow, and back show unexpected behavior. Some regions warm gradually over hours of illumination, suggesting high thermal inertia, heat capacity sufficient to store energy and resist rapid temperature changes. Other regions respond almost instantaneously to illumination changes, heating and cooling on timescales of minutes, suggesting negligible heat capacity or extremely efficient radiative coupling. The variations don't correlate with visible features or albedo patterns. Bright regions sometimes show high thermal inertia, sometimes low. Dark regions behave unpredictably, each one different, as if surface properties vary independently of composition, as if structure and texture determine thermal response more than the chemical nature of the materials. The thermal models attempt to match observations by adjusting parameters surface roughness, grain size, porosity, conductivity, emissivity. The parameter space expands into dozens of dimensions, each variable affecting predicted temperatures in different ways, each one uncertain and difficult to constrain independently. The fitting algorithms search for parameter combinations that minimize disagreement between predictions and measurements, that produce temperature maps resembling the observed patterns. Some solutions exist, parameter sets that technically fit the data within uncertainties. But the solutions require extreme values, unrealistic combinations, properties that don't occur naturally or that contradict other observational constraints. The models fit mathematically but fail physically, describe surfaces that cannot exist under normal conditions. The emission spectrum in mid-infrared wavelengths shows features that might indicate mineralogy, that might reveal silicate compositions through characteristic absorption bands. But the features are weak, ambiguous, possibly artifacts of processing or atmospheric contamination or instrumental responses. The researchers attempt spectral unmixing, trying to separate contributions from different surface components, trying to identify the materials that combine to produce the observed thermal emission. the unmixing fails to converge, generates non-unique solutions, suggests mixtures that vary depending on starting assumptions or regularization choices. The composition remains indeterminate, hidden beneath uncertainties that no amount of additional observation seems to reduce. Only actual atoms and molecules compose the surface. Only real materials with real thermal properties determined by quantum mechanics and statistical thermodynamics. The strange temperature distributions must arise from actual physical processes, from genuine features of the surface's structure and composition. The object doesn't violate thermodynamics. It doesn't break conservation of energy. It simply possesses properties that fall outside the range sampled by previous observations, that differ enough from normal solar system materials to make standard models inapplicable. The thermal anomalies indicate unfamiliarity, not impossibility. They suggest that human experience with natural surfaces remains limited, that the diversity of materials existing in the universe exceeds the catalogue assembled from studying a few hundred asteroids and a few dozen comets in one small planetary system around one ordinary star. The hypothesis appears first in a preprint, uploaded to an open-access server where researchers share results before peer review. The abstract states carefully that conventional explanations fail to account for the ensemble of anomalous properties, that the object's characteristics remain unexplained within the framework of natural formation processes. The paper reviews the observational evidence, the extreme elongation, the absence of outgassing, the wavelength-dependent albedo, the thermal anomalies, the geometric surface features. It argues that each anomaly might be explained individually through improbable but natural mechanisms, but that the combination of all anomalies together strains credulity, requires invoking too many unlikely circumstances occurring simultaneously in one object. The paper proposes an alternative interpretation. It suggests that 3I/Atlas might be artificial, manufactured rather than naturally formed, a product of technological activity rather than planetary accretion or cometary condensation. The language remains tentative, hedged with qualifications and caveats, acknowledging the extraordinary nature of the claim and the extraordinary evidence that would be required to support it convincingly. The authors present the hypothesis not as a conclusion but as a possibility worth considering, a framework that might organize the disparate observations into a coherent narrative where natural explanations fragment into incompatible special cases. The argument proceeds through elimination. Natural objects formed through gravitational collapse show roughly spherical or ellipsoidal shapes, not extreme elongation exceeding 10:1 aspect ratios. Natural objects composed of ices show outgassing when heated, not complete inactivity across all volatile species. Natural surfaces weathered by billions of years of cosmic ray exposure show uniform properties, not geometric patterns and sharp compositional boundaries. Natural thermal properties follow from material composition, not from spatial variations that require invoking layered structures or exotic thermal conductivities. Each observation individually might be reconciled with natural processes through creative modelling. But the totality suggests something else, suggests design rather than accident, suggests structure imposed by intent rather than emerging from physical law. The paper carefully avoids sensationalism. It does not claim to have discovered alien technology. It does not interpret the geometric features as writing or symbols or communication attempts. It simply notes that the object's properties align more closely with expectations for manufactured structures than for natural bodies, that spacecraft and probes and artificial satellites exhibit similar characteristics, controlled shapes, varied surface materials, thermal management systems, absence of volatile outgassing, structural integrity maintained through engineering rather than gravitational equilibrium. The comparison is not proof, merely observation that one category fits better than the other, that artificial origins explain more with fewer special assumptions than natural origins require. Only one previous interstellar object prompted similar speculation. Oumuamua, with its extreme shape and non-gravitational acceleration, generated papers suggesting artificial origins, discussing possibilities of light sails or derelict probes, entertaining hypotheses that mainstream astronomy largely rejected. The scientific community responded with criticism, with alternative natural explanations, with reminders about Occam's razor and the principle that extraordinary claims require extraordinary evidence. The artificial hypothesis for Oumuamua never gained traction, never convinced more than a handful of researchers, eventually faded into the literature's margins, as attention moved to other topics and the object itself faded beyond observational reach. The media discovers the preprint within hours. News articles appear with headlines that strip away the paper's careful qualifications, that transform tentative suggestions into definitive claims. Scientists say interstellar object could be alien probe. New evidence suggests 3I/Atlas is artificial. Harvard researchers' interstellar visitor shows signs of technology. The stories spread through social networks, accumulate shares and comments and speculation that far exceeds the actual content of the scientific paper. The researchers give interviews, attempt to restore nuance, emphasize uncertainties and alternative possibilities. The message that reaches public consciousness simplifies into binary categories: natural or artificial, random or designed, evidence of alien civilizations or just another rock. The scientific community reacts with skepticism. Other researchers publish responses, rebuttals that defend natural explanations, that argue the anomalies are not as severe as claimed, that demonstrate how each unusual property might arise from conventional processes under specific conditions. The responses invoke rare but possible scenarios: tidal disruption creating extreme elongation, organic mantles suppressing outgassing, impact processes creating geometric fracture patterns, heterogeneous accretion producing varied surface compositions. The explanations feel forced, require stacking unlikely events, but remain technically possible within known physics. The debate polarizes, divides into camps that interpret the same data through different philosophical frameworks, different priors about what kinds of objects should exist in the universe. Only time and more observations might resolve the debate. Only additional data, higher resolution images, spectroscopic measurements at wavelengths not yet explored might provide evidence that definitively favors one interpretation over others. But 3I/Atlas continues moving, continues fading, approaches the observational limits where even the largest telescopes lose the ability to distinguish signal from noise. The window for detailed study closes gradually, day by day, as the object recedes toward interstellar space. Whatever the truth about its nature, that truth will soon become unreachable, preserved only in the archival data collected during these few months of visibility, in the images and spectra and photometry that must contain all the evidence that will ever exist for evaluating hypotheses about what this thing is and where it came from, and whether it represents the natural products of cosmic evolution or something else entirely. The scientific response arrives in multiple papers, published through standard peer review, appearing in established journals where editorial oversight filters speculation from evidence. The first paper addresses the elongation problem, arguing that tidal disruption during a close stellar encounter could stretch objects into extreme shapes, that the stresses from differential gravitational forces might pull material along the tidal axis, while compression occurs perpendicular to it. The calculations show that objects passing within a few stellar radii of their host star, particularly fast rotating stars with strong equatorial bulges, could experience forces sufficient to create aspect ratios exceeding 10:1 before ejection into interstellar space. The mechanism is rare but not impossible, requiring specific encounter geometries and material properties, but remaining within the bounds of conventional astrophysics. The second paper tackles the outgassing problem through a different mechanism. It proposes that 3a/Atlas might be composed primarily of hydrogen ice, a material that rarely occurs in the solar system but could form in the coldest regions of protoplanetary disks or in molecular clouds. Hydrogen ice sublimates at extremely low temperatures, would have vaporized from surface layers long ago during the interstellar journey. But beneath a thin refractory crust, hydrogen ice might persist, insulated from external heating, maintaining temperatures near absolute zero through efficient thermal isolation. The hydrogen outgassing would occur but remain undetectable, producing no emission lines in visible wavelengths, creating thrust-through escaping gas that instruments cannot observe directly. The hypothesis is creative, explains both the lack of detectable activity and the non-gravitational acceleration, requires only that interstellar space can produce and preserve exotic ices. The third paper addresses the surface features through impact physics, arguing that geometric patterns can emerge from fracture networks created during high-velocity collisions. The authors simulate impacts at various angles and velocities, model how stress waves propagate through elongated bodies, demonstrate that certain impact geometries create fracture patterns with regular spacing and parallel orientations. The simulations produce images that superficially resemble the observed features, show linear structures and discrete patches that result purely from mechanical failure modes in stressed materials. The resemblance is not perfect, requires selecting specific impact parameters and viewing angles, but establishes that geometric features need not imply artificial origins. The fourth paper examines the thermal anomalies through surface heterogeneity, proposing that 3a/Atlas accreted from multiple protoplanetary bodies with different compositions, that the surface represents a collage of materials with varied thermal properties. The paper calculates how mixtures of high and low thermal inertia materials create complex temperature distributions, how boundaries between different compositions remain sharp when heat conduction is minimal in vacuum conditions. The model matches some aspects of the observations, explains spatial temperature variations through natural compositional gradients, demonstrates that strange thermal behavior does not require exotic processes or artificial structures. Only standard physics appears in these papers, only conventional mechanisms, rare but possible, invoked to explain observations that initially seemed inexplicable. The explanations accumulate, each one addressing a different anomaly, together forming a framework where natural processes account for all the unusual properties without requiring technological manufacture. The framework feels incomplete, requires combining multiple unlikely events, tidal disruption and hydrogen ice composition, and specific impact geometries and heterogeneous accretion, all occurring in one object. The probability of all these factors coinciding seems low, but low probability is not impossibility. Rare events happen eventually in a large universe given sufficient time and sufficient opportunities. The artificial hypothesis loses ground in the literature, becomes increasingly marginalized as natural alternatives proliferate. The researchers who proposed artificial origins defend their position, argued that the natural explanations are collectively more improbable than a single technological explanation, that Occam's razor actually favors the artificial hypothesis when all factors are considered. But scientific consensus gravitates toward conservatism, toward explanations that don't require revising fundamental assumptions about what exists in the universe. Artificial intelligence from other civilizations remains hypothetical, unproven, unsupported by any direct evidence despite decades of searching. Natural objects, however strange, remain firmly in the realm of the known, the confirmed, the consistent with existing theory. The debate continues in conferences, in email exchanges between research groups, in the comment sections of preprint servers where scientists argue over interpretation and methodology. The tone remains professional but reveals underlying tensions, different philosophies about how science should respond to anomalies, different thresholds for abandoning conventional frameworks in favor of radical alternatives. Some researchers advocate for the artificial hypothesis, not because they believe it definitively, but because excluding it a priori seems unscientific, seems to bias investigation toward comfortable conclusions rather than following evidence wherever it leads. Others argue that entertaining artificial hypotheses without compelling evidence wastes resources, encourages speculation over rigorous analysis, damages the credibility of the field. Only the object itself contains the answer. Only the actual atoms and structures that compose it know whether they were arranged by natural processes or deliberate design. The distinction might not even be meaningful. Natural processes follow deterministic laws, produce outcomes that might include complex organization, might generate structures that appear designed but emerge purely from physics and chemistry operating over cosmic timescales. Life itself is natural, emerges from chemistry, yet produces technology. The boundary between natural and artificial blurs when technological civilizations are themselves products of nature, when their artifacts represent one possible outcome of stellar and planetary evolution, just as rocks and ice represent other outcomes. The higher resolution observations arrive from a space telescope repositioned to target 3Y/Atlas during its closest approach. When apparent size reaches maximum and photon flux peaks, the telescope operates in visible wavelengths with adaptive optics that correct for residual jitter in the spacecraft's pointing, achieving resolution near the diffraction limit, revealing surface details at scales approaching tens of meters. The exposure times extend for hours, stacking multiple frames to suppress noise, building signal strength sufficient to detect subtle features that earlier observations could only hint at. The processing pipeline removes cosmic ray hits, corrects for geometric distortion, sharpens the point spread function through deconvolution algorithms that recover high-frequency information. The images reveal structure, not just brightness variations or color differences, but actual geometric structure visible at the resolution limit. Linear features running parallel across sections of the surface, each line perhaps 20 or 30 meters wide, separated by gaps of similar dimensions. The lines maintain consistent spacing across fields of view that span hundreds of meters, show straightness that appears inconsistent with random fracturing or impact processes. The lines don't curve around topography, don't follow gravitational or stress patterns, don't show the degradation and irregularity that erosion produces over geological time. They look maintained, preserved, arranged according to logic that natural weathering doesn't follow. The surface shows patches of uniform brightness, regions with sharp boundaries where reflectivity changes abruptly from high to low. The boundaries are straight in some locations, right-angled in others, forming rectangular shapes that span dozens of meters on each side. Natural surfaces show gradational changes, smooth transitions where different materials mix, or where space weathering affects composition gradually across spatial scales. These boundaries show none of that blending, maintain sharpness that suggests different materials meeting at discrete interfaces, suggests layered construction rather than gradual accretion or modification. The rectangular patches organize into larger patterns, arrangements that show symmetry, repetition, spacing that remains consistent despite the object's tumbling rotation. The enhanced images circulate through research networks within days. The teams who captured the data publish the raw files openly, inviting independent analysis, encouraging other researchers to process the images using different techniques, different assumptions, different approaches that might reveal features or artifacts the original processing missed. Some analysts enhance the linear features, apply edge detection filters that highlight boundaries and sudden brightness changes. The lines become more prominent, more clearly structured, more difficult to dismiss as image artifacts or processing errors. Other analysts attempt to remove the features, applying smoothing filters or modeling them as systematic errors in the telescope's optical system. The features persist, appear in multiple independent frames captured at different times and viewing angles, remain present regardless of processing choices. Only photons carry information about surface structure at these distances. Only electromagnetic radiation bridges the gap, brings messages encoded in brightness patterns in the spatial distribution of a reflected sunlight. The images represent reality, correspond to actual surface features that exist on the object regardless of whether observers understand them. The features are real in the same sense that mountains are real, that craters are real, that any topography detected through remote sensing is real. The question is not whether they exist, but what they mean, whether they result from natural geological processes or from something else, whether their organization implies randomness or design. The published analysis papers approach the features cautiously. The authors describe what they see without interpreting what it means, list measurements and statistics without drawing conclusions about origins. The features show periodicity, regularity, symmetry, all quantifiable properties that characterize the patterns objectively. The papers report aspect ratios, spacing distributions, orientation angles, all the geometric properties that define shape and arrangement. The measurements are precise, reproducible, confirmed across multiple analysis pipelines and multiple research groups. The measurements exist as facts, independent of interpretation, available for anyone to verify or dispute through examination of the archived data. The natural explanation attempts expand to accommodate the new observations. Perhaps the linear features are layered strata, exposed by impacts, bedding planes that formed during initial accretion and now appear as parallel lines where erosion or outgassing removed overlying material. Perhaps the rectangular patches represent different ice phases that crystallized in geometric patterns during thermal cycling, structure that emerges naturally when materials freeze and thaw under conditions found in interstellar space. Perhaps the symmetry is coincidental, pattern recognition imposing order on arrangements that are actually random but happen to look organized when viewed from specific angles at limited resolution. The artificial hypothesis gains renewed attention. The higher resolution images provide exactly the kind of evidence that proponents argued was necessary direct observation of surface structure at scales where natural versus artificial origins might be distinguished. The rectangular patches look like panels. The linear features look like seams or joints or structural elements. The organization looks like engineering, like components arranged according to function rather than scattered according to random processes. The resemblance to human-made objects is striking. The similarity to spacecraft surfaces or modular construction apparent to anyone familiar with aerospace engineering. The resemblance is not proof, but it strengthens the case that artificial origins deserve consideration alongside natural alternatives. Only each new image deepens the mystery rather than resolving it. Only each improvement in resolution reveals more structure, more detail, more features that demand explanation and resist simple categorization. The object should become clearer with better data, should fit more comfortably into known categories as knowledge increases. Instead, it becomes stranger, more anomalous, more resistant to conventional interpretation. The mystery grows with each observation, accumulates with each measurement, persists despite intensive study and multiple theoretical frameworks attempted and discarded. Whatever this thing is, it does not want to be understood easily, does not surrender its nature to casual inquiry, continues hiding its truth behind ambiguous evidence that supports multiple contradictory conclusions with equal plausibility. The trajectory analysis traces the object's path backward through galactic space, unwinding its motion across millions of years, projecting where it traveled before entering the solar system's gravitational influence. The calculations require precise measurements of position and velocity, require accounting for gravitational perturbations from planets encountered during its passage, require correcting for the non-gravitational acceleration that affects its orbit in ways that gravity alone cannot explain. The orbital integration software runs on supercomputers, simulating the motion through time-reversed equations, following the object's path as it retreats from the Sun, exits the planetary region, crosses the heliopause, enters the interstellar medium where only galactic gravity and stellar radiation pressure affect trajectories. The origin point remains uncertain. The errors in velocity measurements, small but non-zero, propagate backward through time, expanding into volumes of space that grow larger with increasing temporal distance. Trace the trajectory back 1 million years and the uncertainty spans several light years. Trace it back 10 million years and the probable origin region encompasses hundreds of cubic light years, volumes containing dozens of stellar systems, any one of which might have been the object's home before some event ejected it into interstellar wandering. The calculations cannot identify a specific source, cannot point to one star and say definitively that 3A/Atlas came from there. The stellar catalogue provides context. The region of space corresponding to the object's origin contains mostly unremarkable stars, red dwarfs that burn slowly for trillions of years, offering stable environments but dim illumination. A few yellow stars similar to the Sun, middle-aged and ordinary, possessing nothing that distinguishes them from millions of others scattered through this galaxy. Several brown dwarfs, failed stars too small to ignite fusion, glowing only in infrared from residual heat remaining from their gravitational collapse. No massive stars, no supernovae remnants, no stellar nurseries where planets currently form from collapsing molecular clouds. Just old, quiet, stable systems where planetary evolution might have proceeded for billions of years without dramatic interruption. Only galactic rotation complicates the backtracking. Stars orbit the galactic center at speeds approaching 200 kilometers per second, completing orbits every few hundred million years. Over the 10 million years that 3A/Atlas might have been traveling, the stellar neighborhood it came from has moved significantly, orbited partway around the galaxy, shifted position relative to the Sun's current location. The calculations must account for this motion, must transform coordinates between the present stellar configuration and the configuration that existed when the object began its journey. The transformations add uncertainty, make identifying specific source stars even more difficult, blur the origin into statistical distributions rather than definite locations. The object's velocity vector points roughly toward the constellation Sagittarius. But that direction reflects where it's going more than where it came from. The trajectory calculations suggest it arrived from the direction of Cygnus, descending toward the solar system from above the galactic plane, falling inward from the halo regions where stars thin out and interstellar space dominates. The path doesn't intersect any known stellar systems along its probable route. It traveled through empty regions, light years from the nearest star, crossing voids where only diffuse gas and dust exist to interact with passing objects. For millions of years, it moved through darkness, through cold approaching absolute zero, through radiation fields that slowly erode surfaces and break down complex molecules. The travel time estimates depend on assumptions about when and how the object was ejected from its source system. If it left 10 million years ago, traveling at its current velocity, it covered roughly 300 light-years, a substantial distance, but small compared to the galaxy's 100,000 light-year diameter. If it left more recently, a few million years ago, the source must be closer, within 100 light-years, limiting possibilities to a smaller volume of space that contains fewer candidate stars. If it left longer ago, tens of millions of years, the uncertainties grow so large that determining origins becomes impossible with current measurement precision. The object could have come from anywhere in a local galactic neighborhood, could have travelled thousands of light years, could have originated in stellar systems that no longer exist in the configurations they held when the journey began. Only gravity and radiation pressure affected the journey. Only the gentle forces that pervade interstellar space, insufficient to alter trajectories significantly, but enough to accumulate small changes over millions of years. No stellar encounters, no planetary flybys, nothing that would perturb the orbit dramatically or leave signatures visible in the current trajectory. The path appears clean, simple, a nearly straight line through space modified only by the galaxy's overall gravitational field. The simplicity suggests the object travelled alone, didn't participate in any close encounters with other bodies, maintained its course without assistance or interference from external forces beyond the minimal background present everywhere in the galaxy. The statistical models calculate probabilities, given the density of stars in this region of the galaxy, given the rate at which planetary systems eject objects through gravitational interactions, given the velocities typical of ejected bodies. What is the probability that an object like 3/8 exists and happens to pass through the solar system during the brief window of human civilization? The probabilities are low, but not vanishingly small. Perhaps one interstellar object of this size crosses the inner solar system per decade. Humanity has been watching carefully for only a few years, has detected only 3 such objects, has missed countless others that passed unobserved. The detection might represent luck, or it might indicate that interstellar objects are more common than population models suggest, that the galaxy contains more wanderers than simple ejection rates predict. The brightness fades gradually, predictably. Following the inverse square law as distance from both Sun and Earth increases, the object moves outward past Mars' orbit, past the asteroid belt, heading toward the outer solar system where sunlight weakens and surface temperatures drop toward the equilibrium values of deep space. The telescopes track it as long as possible, extracting signal from noise through longer exposures, through stacking more frames, through increasingly aggressive processing that risks introducing artifacts in the desperate attempt to maintain detection. The signal-to-noise ratio declines week by week, the object becoming indistinguishable from background fluctuations, from the photon statistics that limit all astronomical observations. The final images arrive from the largest telescopes, instruments with mirrors 10 meters across, light-gathering power sufficient to detect objects 1 billion times fainter than naked eye visibility. Even these instruments struggle as 3I/Atlas recedes beyond Jupiter's orbit, beyond Saturn, approaching the distances where only reflected sunlight from the giant planets themselves remains easily detectable. The object appears as barely more than a statistical excess, a few pixels slightly brighter than the surrounding field, brightness that might be real or might be random variation in the detector noise. The astronomers debate whether the last detections are genuine or whether they've crossed the threshold where wishful thinking sees patterns in randomness. The observing campaigns conclude with a final coordinated session, multiple telescopes pointing simultaneously at the predicted position, attempting one last detection before the object fades permanently beyond human capability to observe. The exposures extend for hours, integrating photons across the entire night, combining data from different sites to suppress noise through averaging. The combined image shows nothing definitive, only a marginal excess at the expected location, a signal consistent with the object's presence but also consistent with statistical fluctuation in an empty field. The teams mark this as the final observation, acknowledge that further attempts will yield no useful information, except that 3I/Atlas has escaped into the darkness from which it came. Only archival data remains. Only the measurements collected during those few months of visibility, the images and spectra and photometry stored in databases, preserved for future analysis when better models or new theoretical frameworks might extract insights that current understanding cannot achieve. The data sits frozen, unchanging, containing whatever information it contains, ready to answer questions that haven't yet been formulated. Astronomers will return to it, occasionally, checking measurements against new hypotheses, reprocessing images with improved algorithms, searching for details missed during the initial analysis. The object itself continues moving, unreachable and unobservable, but the light it reflected during its passage remains preserved in silicon memories. The trajectory projections extend into the future, calculating where 3I/Atlas will travel over coming centuries and millennia. It will cross Neptune's orbit in 3 years, reach the heliopause in about 50 years, enter the Oort cloud's inner edge in several thousand years. By that time, humanity might have developed telescopes powerful enough to detect it again, space-based observatories located far from Earth's noise and light pollution, instruments sensitive enough to track individual objects across interstellar distances, or perhaps not. Perhaps 3I/Atlas will simply fade into permanent invisibility, join the countless other objects drifting through the galaxy unobserved and unrecorded, known only through the brief encounter that occurred during this particular moment in human history. The velocity ensures escape. No force will turn 3I/Atlas around. No gravitational attraction will capture it into permanent orbit. No planetary encounter will deflect it back toward the inner solar system. The object is leaving, irreversibly, following a trajectory that leads outward into the interstellar medium, toward whatever lies beyond the Sun's gravitational influence. In 100,000 years it might pass near another star, might fall into another planetary system, might be detected by other observers who will puzzle over its properties and debate its origins, just as human astronomers have done. Or it might travel forever through the empty spaces between stars, never approaching anything closely enough for detection, moving through the galaxy as one more piece of debris among trillions. Only the mystery accompanies it, only the unanswered questions, the unresolved debates about its nature, the uncertainty about whether it represents natural processes or something else. The object carries these questions away, takes them beyond the reach of human investigation, ensures that the truth about its composition and structure and origins will remain forever inaccessible unless some future civilization intercepts it with spacecraft capable of matching its velocity, capable of approaching closely enough for direct examination. The probability of such interception seems negligible, the resources required vastly exceeding any practical return, the object likely to remain unsampled and unexplored despite the intense curiosity it generated during its brief visibility. The scientific literature archives the debate. The papers remain available, documenting the observations, the competing hypotheses, the arguments for natural versus artificial origins. The conclusions fragment across multiple positions, some researchers convinced of natural explanations, others maintaining that artificial origins remain viable, most acknowledging uncertainty, admitting that the data permits multiple interpretations without definitively favouring any single framework. The mystery becomes a footnote, a historical curiosity, an example of the ambiguities that arise when observations probe the boundaries of known phenomena. When familiar categories fail to accommodate unfamiliar objects, only time might resolve what observation cannot. Only the accumulation of similar detections, the discovery of additional interstellar objects showing comparable anomalies, might eventually reveal whether 3I/Atlas represents an unusual but natural class of bodies or something genuinely unprecedented. If other objects show similar properties, extreme elongation, lack of outgassing, geometric surface features, the pattern might suggest natural processes that current theory doesn't include, might motivate development of new formation models that accommodate observed characteristics. If no similar objects appear in decades of future surveys, 3I/Atlas might remain unique, singular, an isolated anomaly that defies categorization and persists as a permanent mystery in the astronomical record. The data archives preserve everything: the raw telescope images, the calibration frames, the processing logs that document every transformation applied to convert photons into publishable measurements. The spectroscopic observations sit in standardized formats, wavelength arrays paired with flux values and uncertainty estimates. The photometric light curves span multiple filters and multiple observation sessions, tracking brightness variations across weeks of continuous monitoring. The orbital elements exist as tables of numbers, position and velocity components with timestamps and error bars. Everything is stored, backed up across multiple servers, made publicly accessible through data repositories that astronomers worldwide can query and download. The analysis software sits in version control systems, code repositories that track every line written to process the observations, to fit models, to generate figures appearing in published papers. Other researchers can retrieve the code, run it on the archived data, verify that published results are reproducible. The conclusions follow legitimately from observations rather than from errors in analysis pipelines. The transparency is intentional, part of scientific practice, ensuring that claims can be checked, that mistakes can be found and corrected, that knowledge builds on verifiable foundations rather than on assertions that cannot be independently evaluated. The discussions continue in smaller forums now, among specialists who maintain interest after public attention moves elsewhere. Email threads exchange ideas about reprocessing strategies, about alternative models not yet attempted, about statistical tests that might distinguish between competing hypotheses. The conversations remain technical, focused on methodology rather than interpretation, on extracting maximum information from limited data rather than on arguing about what that information means. The researchers who invested months in observing campaigns continue analysing, continue searching for patterns or correlations that earlier examination missed, continue hoping that some insight will emerge to clarify what 3I/Atlas actually is. Only questions remain accessible now that the object itself has vanished. Only the puzzles that observations revealed without solving, the mysteries that measurements quantified without explaining. The extreme elongation persists as unexplained anomaly, shape that natural processes struggle to maintain, geometry that might indicate structure rather than accident. The absence of outgassing remains puzzling, inactivity that contradicts expectations for icy bodies heated by solar radiation, behavior that requires special compositions or special thermal properties not commonly found in nature. The surface features stay ambiguous, patterns that look organized but might result from natural fracturing, arrangements that suggest design but cannot prove it. The thermal properties defy simple interpretation, temperatures and spatial distributions that don't match standard models, observations that require surface heterogeneity or exotic materials or processes not yet understood. The albedo variations span wavelengths in ways that single-component surfaces cannot explain, require mixing or layering or compositional gradients that themselves demand explanation. The non-gravitational acceleration continues in the trajectory data, subtle forces that perturb the orbit without producing detectable outgassing, motion that conventional physics explains only through implausible mechanisms. Each anomaly might have natural explanation. Together they accumulate into a profile that resists comfortable categorization. The papers conclude with standard academic phrases: further observations are needed. Additional data would constrain models. Future interstellar objects might clarify whether these properties are common or unique. The language acknowledges limitations, accepts uncertainty, avoids claiming definitive conclusions from ambiguous evidence. Science proceeds incrementally, builds understanding through accumulated observations, requires patience and caution when confronting phenomena that don't fit established frameworks. The responses to 3I/Atlas follow this pattern, remain appropriately tentative, resist the temptation to overinterpret limited data or declare victory for any particular hypothesis. Only the object knows its own nature. Only the actual structure, hidden inside the tumbling body now billions of kilometers away and receding, contains the truth that observations approximate but cannot definitively determine: the atoms that compose its bulk, the molecules that form its surface, the arrangement of materials that produces its optical and thermal properties. All these exist in specific configurations that follow from the object's history, from how it formed and what it experienced during millions of years traveling through space. That history is real, determinate, unambiguous, but it remains inaccessible to observers who possess only reflected light and derived quantities, who cannot touch or sample or dissect the object to reveal its internal structure. The telescopes turn to other targets. The observers who tracked 3I/Atlas return to their regular programs, their surveys for asteroids and variable stars and distant galaxies. The computer time allocated for processing and modeling gets reassigned to other projects, other mysteries that offer better prospects for resolution through continued study. The funding cycles move forward. Proposal reviews prioritize research with clearer paths to answers, with questions that data can realistically address within available resources. 3I/Atlas becomes a historical case, an interesting example, a cautionary tale about the limits of remote sensing when confronted with objects that refuse to behave as theory predicts. Only memory preserves the experience of those months when something strange crossed through human awareness, when an object from beyond arrived briefly and departed forever, leaving more questions than answers, more mystery than understanding. The astronomers who observed it remember the excitement of anomalous data, the frustration of failed models, the debates about interpretation that never reached consensus. The object passes into the catalogue of unresolved phenomena, joins other mysteries that astronomy has encountered and documented without explaining unusual transients, anomalous signals, objects that appeared once and never again, observations that don't quite fit and probably never will unless luck or persistence eventually reveals similar cases that together form patterns too clear to dismiss. The stars continue their ancient motions, orbiting the galactic centre at velocities that will carry them through thousands of light years over millions of years, drifting through space along paths determined by gravity and initial conditions set when the galaxy first condensed from primordial gas. The Sun follows its own orbit, circling the centre roughly once every 230 million years, carrying its planetary system through regions of varying stellar density, through spiral arms and interarm voids, through environments that change slowly across geological time. 3I/Atlas moves differently now, no longer bound to any star, travelling on a trajectory that will never close, never repeat, never return to any location it has already passed. The interstellar medium surrounds it. Hydrogen atoms scattered thinly through the vacuum, a few particles per cubic centimetre, essentially nothing by terrestrial standards but sufficient over light years to exert drag, to erode surfaces, to gradually slow objects moving through it. Cosmic rays penetrate everything, high-energy particles accelerated by supernova shocks and magnetar flares, radiation that deposits energy into materials it encounters, breaks chemical bonds, damages crystal structures, ages surfaces at rates measured in millions of years. The object experiences all of this, continues its slow transformation under conditions that exist between stars, continues becoming whatever interstellar objects become when given enough time. The galaxy contains perhaps 100 billion stars, each one potentially harbouring planets, each planetary system potentially ejecting objects through gravitational interactions during formation or evolution. The ejected bodies travel outward, some remaining loosely bound in distant clouds, others achieving escape velocity and departing permanently into interstellar space. The number of such wanderers might exceed the number of bound objects, might mean that most solid matter in the galaxy exists between stars rather than around them, invisible and uncounted, except for the rare occasions when one passes close enough to an observer to be noticed. Darkness and distance reclaim 3I/Atlas. The object becomes invisible, untrackable, one more piece of cosmic debris among incomprehensible numbers. Its brief moment of human attention concluded, its passage through the solar system already receding into the past. The light it reflected continues travelling outward at the speed that light travels, carrying information about its surface away from Earth, propagating images into space where no observers exist to receive them. The images fade and disperse, photons scattering across the expanding sphere of the light cone, until the information becomes too diluted to reconstruct, until quantum noise overwhelms signal, until the memory of what the object looked like dissolves into the background radiation that fills the universe. Somewhere in the immense dark between here and the next star, something tumbles forward through the silence. It carries its shape, its composition, its mysterious geometry outward into regions where no telescope will ever follow. It moves according to laws that never change, following trajectories that conservation principles guarantee, obeying physics that operates identically everywhere regardless of whether observers exist to verify or comprehend. The object knows nothing of human curiosity or human confusion. It simply continues, patient and eternal, crossing the galaxy at velocities too slow to notice across human lifetimes, too persistent to stop across cosmic time. Sleep finds what watching cannot. Rest accepts what analysis struggles to determine. The mind quiets, releasing questions that have no answers, letting mysteries remain mysterious, allowing the universe its secrets and its silence. The object recedes. The stars turn slowly overhead. The darkness between them stretches forever, patient and vast, holding everything that moves through it without judgment or explanation, without need for meaning or purpose beyond simple existence.